Hello there, and welcome. Tonight I want to take you somewhere special, somewhere that exists at the very heart of everything we can see in the cosmos, yet remains one of the most profound mysteries we've ever encountered. It's a place where time moves differently, where gravity writes its own rules, and where darkness itself becomes a kind of anchor for light. Tonight we're going to explore together why every galaxy, from the smallest dwarf to the grandest spiral, seems to harbour a supermassive black hole at its centre, like a quiet secret that the universe has been keeping since nearly the beginning of time itself. Before we drift deeper into this cosmic mystery, I want to create a moment of connection here in the darkness. Perhaps you're lying in bed right now, the day's worries finally beginning to settle like dust in starlight. Maybe you're listening with headphones, creating your own private universe of sound. Wherever you are, whatever time zone cradles you at this moment, you're part of this exploration. If you'd like to share where you're listening from, what time it is in your corner of our small world, I'd love to know in the comments below. There's something beautiful about knowing that while we all look up at the same stars, we see them from different places at different hours, yet we're all part of the same cosmic story. And if this journey into the peaceful mysteries of space brings you the kind of calm you're seeking tonight, perhaps you'd consider subscribing, so we can meet here again, in this quiet space between waking and sleeping, between Earth and the infinite. It's a question that seems too vast for bedtime, doesn't it? Why would nature place something so dense, so gravitationally extreme, at the centre of these beautiful cosmic islands we call galaxies? And yet, perhaps the night is exactly the right time to hold such questions. In the darkness, our minds open differently. We become more receptive to mystery, more comfortable with not knowing everything immediately. The urgency of day fades, and we can simply wonder, without needing to solve everything before dawn. What if, just maybe, the secret at every galactic centre is less a monster and more a memory? What if these supermassive black holes are not cosmic accidents, but fundamental threads in the tapestry of how galaxies form, live, and breathe across billions of years? Tonight, we're going to explore this possibility together, gently, without rush, letting the mystery unfold like a flower that only blooms in darkness. Consider for a moment the scale of what we're discussing. Our own galaxy, the Milky Way, stretches across 100,000 light-years. If you could travel at the speed of light itself, it would take you 100 millennia to cross from one edge to the other, and there, at the very centre, sits something called Sagittarius A, a supermassive black hole, with the mass of 4 million suns compressed into a region smaller than the orbit of Mercury. It's been there, quietly, for most of our galaxy's existence, and stars have been dancing around it for billions of years, tracing out elegant orbits that we've only recently learned to see. But here's what makes this even more intriguing. It's not just our galaxy. When we look out into the universe with our most powerful telescopes, when we peer into the hearts of distant galaxies, millions and billions of light-years away, we find the same thing. Galaxy after galaxy, each one harbours its own supermassive black hole. Some are millions of times the mass of our Sun, others are billions. They sit there, patient and eternal, at the centres of their cosmic kingdoms, and we're only beginning to understand why. The story we're going to explore tonight isn't one of destruction or cosmic violence, though black holes are often portrayed that way. Instead, it's a story of balance, of cosmic architecture, of how the universe builds its grandest structures around these points of ultimate density. It's a story that connects the largest scales we can imagine to processes happening right now, in this very moment, in galaxies so distant their light is only just reaching us, after travelling for most of the age of the universe. As we begin this journey together, let yourself sink a little deeper into wherever you're resting. Feel the weight of your body settling, your breathing becoming slower and more regular. There's no need to understand everything immediately. We have time. The universe has been working on this mystery for nearly 14 billion years. We can take a few hours to contemplate it together, in the quiet depths of space, between the stars where light takes years to travel from one point of interest to another. The universe keeps its secrets in plain sight. We live in a cosmos where the brightest lights often illuminate the deepest mysteries, and perhaps nowhere is this more true than in the relationship between galaxies and their central black holes. It's a relationship that shouldn't exist according to our everyday understanding of physics. Black holes consume, galaxies create. Black holes represent the ultimate endpoint of gravitational collapse, Galaxies are vast living systems where new stars are born every year, and yet, somehow, these two opposite extremes not only coexist, but seem to need each other in ways we're only beginning to glimpse. Think about this with me for a moment. A galaxy is mostly empty space. If you could shrink our solar system down so that the sun was the size of a grain of sand, the nearest star would be another grain of sand about 4 miles away. That's the scale of emptiness we're talking about. Galaxies are vast clouds of stars and gas and dark matter, held together by gravity but mostly consisting of nothing at all. And yet, at their centres, we find these regions where matter has become so dense that space and time themselves are warped beyond recognition. The discovery of this universal pattern didn't happen all at once. It emerged slowly, like a photograph developing in a dark room, detail by detail, over decades of careful observation. In the 1960s, astronomers began detecting strange radio signals from the centres of some galaxies. These weren't like any radio sources they'd seen before. They were incredibly bright, incredibly compact, and they seemed to be associated with the very cores of galaxies. They called them quasi-stellar radio sources, or quasars, because they looked almost like stars but clearly weren't. As our instruments improved, as we launched telescopes into space and built larger arrays on Earth, the picture became clearer. These quasars were actually the bright accretion disks around supermassive black holes, glowing with the light of matter spiralling inward. But here's what's fascinating. Not all galaxies have active quasars. In fact, most don't. Most galaxies, like our own Milky Way, have quiet central black holes, ones that aren't actively feeding, that sit there like sleeping giants while the galaxy spins around them. This raises a beautiful question that we'll explore throughout our journey tonight. If these black holes aren't constantly feeding, if they're not always active, then what role do they play? Why does nature insist on placing them there, at the centre of nearly every galaxy we examine? Perhaps the answer isn't about what they're doing right now in this moment, but about what they've done over cosmic time and what they might do in the future. Let me share something that might help put this in perspective. Scientists have discovered a remarkable correlation, something so unexpected that when it was first found, many astronomers didn't believe it. The mass of a galaxy's central black hole is directly related to the mass of the galaxy's central bulge of stars. Not the whole galaxy, mind you, just the central region. The black hole typically contains about 1/1000th of the mass of this stellar bulge. This might not sound like much, but the consistency of this ratio across different types of galaxies, across different cosmic epochs, suggests something profound. It suggests that galaxies and their central black holes grow together, that they're connected in some fundamental way that goes beyond mere coincidence. Imagine, if you will, that galaxies and their black holes are like dance partners, moving together through cosmic time. Sometimes one leads, sometimes the other, but they're always connected, always responding to each other's movements. When a black hole feeds and grows, it affects the galaxy around it. When a galaxy undergoes a burst of star formation, it can feed its central black hole. It's a relationship that plays out over millions and billions of years, far too slow for us to watch directly, but we can see the evidence frozen in the positions and motions of stars, in the light from distant galaxies, in the cosmic archaeology that modern astronomy has become. As we continue deeper into this mystery, remember that we're not just talking about abstract cosmic phenomena, we're talking about our own cosmic home. The Milky Way, our galaxy, has its own supermassive black hole. We've named it Sagittarius A because it sits in the direction of the constellation Sagittarius, and the asterisk denotes that it's a special kind of radio source. It's about 26,000 light-years away from us, safely distant, quietly sitting at the centre of our galaxy's spiral structure. For most of human history, we didn't even know it was there. Our ancestors looked up at the night sky and saw the band of the Milky Way stretching across the heavens, but they couldn't see its centre. Dust and gas block our view in visible light. It wasn't until we developed radio telescopes, instruments that could peer through this cosmic fog, that we began to realise something massive and invisible lurked at the heart of our galaxy. The story of how we discovered Sagittarius A is itself a testament to human curiosity and ingenuity. In the 1970s and 1980s, astronomers began tracking the motions of stars near the galactic centre. This wasn't easy. These stars are faint, far away, and often hidden behind clouds of interstellar dust. But with patience and increasingly sophisticated instruments, scientists began to map their orbits, and what they found was extraordinary. These stars were moving fast, incredibly fast. Some were travelling at speeds of thousands of kilometres per second. And they were all orbiting around a point, an invisible point where nothing could be seen but where something massive clearly resided. Year after year, observation after observation, the evidence mounted. The only thing that could cause stars to move like this, the only thing massive enough and compact enough, was a black hole. Not just any black hole, but a supermassive one, millions of times the mass of our Sun. In 2020, the scientists who led these observations, Reinhard Genzel and Andrea Ghez, were awarded the Nobel Prize in Physics for their discovery. But in a way, the prize wasn't just for finding a black hole. It was for showing us that we live in a galaxy with a dark heart, that our cosmic home is built around one of the most extreme objects in the universe. And more than that, it was for helping us realize that this isn't unusual. This is normal. This is how galaxies are. But let's pull back for a moment and think about what this means on a more personal level. Every atom in your body, except for hydrogen, was forged in the heart of a star. The calcium in your bones, the iron in your blood, the carbon that forms the backbone of your DNA, all of these were created in stellar furnaces and scattered into space when those stars died. You are quite literally made of stardust. And all of those stars, all of that stardust, has been orbiting around Sagittarius A for billions of years. In a very real sense, the supermassive black hole at the centre of our galaxy has been there throughout your entire cosmic history. Every star that contributed to your existence, every cosmic event that led to you being here, listening to these words, happened in a galaxy shaped by the presence of this invisible giant. You could say that Sagittarius A is like a cosmic ancestor, not in the sense that it created you directly, but in the sense that it has always been there, a constant presence in the story of your atoms. This perspective might seem overwhelming at first, but I find it deeply comforting. It means we're part of something so much larger than ourselves, something that has been unfolding for billions of years and will continue long after we're gone. We're not separate from the cosmos, we're woven into its very fabric. The same forces that govern the motion of stars around supermassive black holes govern the molecules in our bodies. We're part of the same physics, the same cosmic dance. As we continue to explore this mystery together, let's also consider how our understanding of these cosmic giants has evolved. Black holes themselves were once considered too strange to be real. When Carl Schwarzschild first solved Einstein's equations in a way that predicted their existence, even Einstein himself was skeptical. The idea that matter could collapse to a point of infinite density, creating a region of space from which not even light could escape, seemed more like science fiction than science fact. But the universe, as we've learned time and time again, is often stranger than our imaginations. Not only do black holes exist, but they come in different sizes. There are stellar mass black holes, formed when massive stars collapse at the end of their lives. These typically have masses between 3 and 20 times that of our Sun. And then there are the supermassive black holes we're discussing tonight, millions or billions of times the Sun's mass. The gap between these two categories is itself a mystery. We don't see many intermediate mass black holes, though we're starting to find some. It's as if nature prefers to make black holes either small or enormous, with not much in between. The question of how supermassive black holes form is one we'll explore in detail as our journey continues. But for now, consider this puzzle. The universe is about 13.8 billion years old. We see supermassive black holes in galaxies when the universe was less than 1 billion years old. How did they grow so massive so quickly? If they started as stellar mass black holes and grew by consuming matter, there hasn't been enough time. It would be like finding a full-grown oak tree in a forest that's only been growing for a few months. This timing puzzle is one of the most active areas of research in modern astronomy. Perhaps these massive black holes formed differently than their smaller cousins. Perhaps the early universe, which was denser and more turbulent than today's cosmos, allowed for processes we don't see anymore. Perhaps massive clouds of gas collapsed directly into black holes without ever forming stars first. Or perhaps the first stars were themselves massive beyond anything we see today, leaving behind black hole seeds hundreds or thousands of times the mass of our Sun. Each possibility opens up new questions, new avenues of investigation, and this is what makes science so beautiful, so endlessly fascinating. Every answer we find reveals new questions, new depths to explore. The universe doesn't give up its secrets easily, But perhaps that's what makes the journey of discovery so rewarding. As you listen to these words, as you contemplate these vast scales and cosmic mysteries, remember that you're doing something remarkable. You're using a brain that evolved to help primates navigate forests and social groups to contemplate the architecture of the universe itself. The fact that we can even ask these questions, that we can build instruments to peer into the hearts of galaxies, that we can trace the invisible through its effects on the visible, is itself a kind of miracle. And perhaps this is part of why the night feels like the right time for these contemplations. In the darkness, when the immediate concerns of our daily lives fade into shadow, we can reconnect with that sense of wonder that makes us human. We can remember that we're explorers by nature, that curiosity is written into our DNA just as surely as the instructions for building our bodies. The relationship between galaxies and their central black holes touches on some of the deepest questions in cosmology. How do structures form in the universe? What role does gravity play versus other forces? How do feedback loops work on cosmic scales? These aren't just abstract academic questions. They're about understanding our cosmic context, about knowing where we fit in the grand scheme of things. Think about feedback for a moment, a concept that will become central to our story. When a black hole feeds, when matter spirals inward and heats up, it doesn't all fall in. Some of it gets blown back out in powerful jets and winds. These outflows can shut down star formation in the surrounding galaxy, which in turn limits how much matter can fall toward the black hole. It's a self-regulating system, like a thermostat that keeps the temperature in a room stable. But this happens over millions of years, over scales so vast that entire civilizations could rise and fall in the time it takes for one pulse of this cosmic feedback cycle. We see the universe in snapshots, frozen moments captured by our telescopes. We have to piece together the movie from these still frames, inferring the action from the positions of the actors. This is where the power of modern astronomy really shines. We can look at galaxies at different distances, which means we're seeing them at different times in the past. Light from a galaxy a billion light-years away shows us that galaxy as it was a billion years ago. By looking at galaxies at various distances, we can see different stages of galactic evolution, like looking at photographs of different people at different ages to understand how humans grow and change. And what we see is remarkable. Galaxies in the early universe look different from galaxies today. They're smaller, more irregular, more actively forming stars. Their central black holes are often more active too, shining as quasars that can outshine the entire galaxy around them. As we look at galaxies closer to us in space and time, we see them settling down, becoming more organized, with their black holes mostly quiet, like Sagittarius A in our own galaxy. This cosmic evolution, this gradual transformation from chaos to order, from activity to quiescence, seems to be universal. It happens in galaxy after galaxy, across the entire observable universe. And at the center of each of these transformations sits a supermassive black hole, like a conductor leading a cosmic orchestra through a piece that takes billions of years to perform. Let me paint you a picture of what we think might be happening. In the early universe, galaxies are rich with gas, the raw material for making stars. This gas can also feed the central black hole, making it shine as a quasar. But the energy from the quasar heats the remaining gas, blowing some of it out of the galaxy entirely and preventing the rest from cooling enough to form new stars. Eventually, the black hole runs out of food and goes quiet. The galaxy can then resume forming stars, but more slowly than before. Over billions of years, this process repeats, with periods of black hole activity alternating with periods of star formation, until eventually the galaxy settles into a stable state, like our Milky Way today. It's a bit like a garden reaching maturity. At first, there's rapid growth, with plants competing for resources, some thriving while others are crowded out. But over time, a balance emerges. The garden reaches a state where growth and decay are balanced, where the ecosystem is stable and self-sustaining. Galaxies, it seems, go through a similar process, with their central black holes playing a crucial role in determining when and how they mature. This cosmic gardening, if you will, happens through processes we're only beginning to understand. When we observe active galactic nuclei, regions where supermassive black holes are actively feeding, we see incredible displays of energy. Jets of particles shoot out from the poles of the black hole at nearly the speed of light, extending for thousands or even millions of light-years into intergalactic space. These jets can be so powerful that they affect not just their host galaxy, but neighbouring galaxies as well. Imagine the scale of this. A black hole, which might be smaller than our solar system, can launch jets that stretch across distances that dwarf entire galaxies. It's like a pinprick creating ripples that spread across an entire ocean. The energy involved is almost incomprehensible, yet it's happening right now in galaxies throughout the universe. But not all black hole feedback is so dramatic. Sometimes it's more subtle, a gentle wind rather than a powerful jet. These winds can still carry enormous amounts of energy, heating the gas in the galaxy and preventing it from cooling and forming stars. It's this gentler form of feedback that might be most important for understanding why galaxies look the way they do today. As we delve deeper into this cosmic mystery, it's worth pausing to appreciate the tools that have made these discoveries possible. The study of supermassive black holes requires some of the most sophisticated instruments ever built. Radio telescopes the size of football fields, infrared cameras that can peer through cosmic dust, space telescopes that orbit above Earth's atmosphere, gravitational wave detectors that can measure distortions in space-time smaller than the width of a proton. Each of these instruments tells us something different about black holes and their host galaxies. Radio telescopes reveal the jets and the accretion disks. Infrared telescopes show us the stars orbiting close to black holes. Optical telescopes map out the structure of galaxies. X-ray telescopes detect the hot gas falling into black holes. And gravitational wave detectors, the newest addition to our toolkit, actually hear the ripples in space-time created when black holes merge. This multi-wavelength, multi-messenger approach to astronomy has revolutionized our understanding of the universe. It's like being able to see, hear, and touch the cosmos all at once. Each sense provides different information, and together they create a rich, detailed picture of cosmic phenomena we could never hope to observe with just one type of instrument. The story of how we've come to understand supermassive black holes is also a story of human collaboration on a global scale. The Event Horizon Telescope, which gave us our first images of black hole shadows, isn't a single telescope but a network of radio dishes around the world working together to create a virtual telescope the size of Earth itself. The scientists analysing the data from these instruments come from dozens of countries, speaking different languages but united by a common curiosity about the universe. This international collaboration extends beyond just the scientists. The funding for these projects comes from governments and institutions around the world. The technology develops through partnerships between universities, national laboratories, and private companies. The knowledge gained is shared freely, published in journals that anyone with an internet connection can access. In a very real sense, our understanding of supermassive black holes is the achievement of our entire species, a testament to what we can accomplish when we work together toward a common goal. As we continue our exploration, drifting deeper into the cosmic night, consider how remarkable it is that we can even have this conversation. A century ago, we didn't know other galaxies existed. We thought the Milky Way was the entire universe. The idea of black holes was pure speculation, a mathematical curiosity with no connection to reality. And now, here we are, mapping the invisible, weighing the unseeable, understanding processes that happen over billions of years and across billions of light years. In the quiet depths of space, time moves like a slow tide and we float upon it. If you compressed the age of the universe into a single day, with the Big Bang at midnight, the first stars would appear around 12:10 a.m. The first galaxies would form by 12:30. Our solar system wouldn't come into existence until about 4 real p.m. All of human history, from the first cave paintings to this very moment, would occupy less than the last second before midnight. This cosmic perspective has a way of making our daily concerns seem small, but not in a way that diminishes us. Rather, it connects us to something eternal, something that transcends our individual lives. We are part of a story that began billions of years before us, and will continue billions of years after. The atoms in our bodies have been on an incredible journey. From the Big Bang through stellar furnaces, through supernovae and planetary formation, to arrive here, now, arranged in just such a way that they can contemplate their own history. And throughout this entire journey, supermassive black holes have been there, shaping the galaxies where this story unfolds. They were there when the first stars formed, growing from seeds we're still trying to understand. They were there during the peak of cosmic star formation, when the universe was ablaze with new suns. They're here now, mostly quiet but still influential, still determining the fate of their galaxies. And they'll be there in the far future, when the universe is cold and dark, the last repositories of mass and energy in a cosmos sliding toward entropy. But let's not get ahead of ourselves. Tonight, we're focused on understanding why these cosmic giants exist at the centers of galaxies, what role they play in the cosmic ecosystem. To truly appreciate this, we need to understand scale in a way that our everyday experience doesn't prepare us for. Consider the Milky Way again. Our galaxy contains between 200 and 400 billion stars. That's more stars than there are grains of sand on all the beaches on Earth. Each of those stars is a sun, many with their own planets, their own possibilities for complexity and perhaps even life. And all of them, every single one, orbits around the center of the galaxy where Sagittarius A resides. But Sagittarius A, massive as it is at 4 million solar masses, contains only about 0.01% of the total mass of the Milky Way. It's like a single grain of sand influencing an entire beach. And yet, its influence is undeniable. The orbits of stars in the central region of the galaxy are entirely determined by its gravity. The history of star formation in our galaxy has been shaped by its activity. The future of the Milky Way will be influenced by how Sagittarius A evolves and interacts with its environment. This might seem paradoxical. How can something so small, relatively speaking, have such a large influence? The answer lies in the concentrated nature of a black hole's mass and the way gravity works. Gravity follows an inverse square law, which means its strength decreases with the square of the distance. But this also means that if you get close enough to a massive object, its gravitational influence becomes overwhelming. Near a supermassive black hole, space and time themselves are distorted. Time runs slower, space is curved. The normal rules of physics that govern our daily lives start to break down. It's a realm where Einstein's general relativity reigns supreme, where the fabric of space-time itself becomes a dynamic, flexible medium that bends and warps in response to mass and energy. This extreme environment near a black hole is also where some of the most energetic processes in the universe occur. When matter falls toward a black hole, it doesn't just disappear, it forms an accretion disk, a swirling maelstrom of gas and dust that heats up through friction to millions of degrees. This disk can shine brighter than all the stars in the galaxy combined. The magnetic fields generated in this disk can accelerate particles to nearly the speed of light, creating the jets we observe shooting out from active galactic nuclei. But here's something beautiful to consider. Most of the time, these supermassive black holes are quiet. Sagittarius A, for instance, is currently in a dormant state. It's not actively feeding, not producing jets, not doing much of anything except sitting there, bending space-time with its presence. It's like a sleeping giant, and our galaxy has organized itself around this slumbering titan. This raises fascinating questions about the relationship between activity and inactivity, between violence and peace in the cosmos. Perhaps the quiet periods are just as important as the active ones. Perhaps galaxies need these times of calm to form stars, to develop complexity, to possibly even evolve life. The fact that we exist, that Earth has been stable enough for billions of years to allow life to evolve and thrive, might be thanks in part to the current quiescence of Sagittarius A. Scientists have found evidence that Sagittarius A wasn't always so quiet. There are hints of more recent activity, perhaps just a few million years ago. Fermi bubbles, enormous structures of hot gas extending above and below the galactic plane, might be remnants of a past feeding event. X-ray echoes bouncing off gas clouds near the galactic center suggest that Sagittarius A might have been more active even just a few hundred years ago. These glimpses of past activity remind us that we're seeing just one frame of a very long movie. The relationship between galaxies and their central black holes is dynamic, changing over cosmic time in ways we're only beginning to understand. What seems permanent and stable to us, living our brief human lives, is actually part of a much longer cycle of activity and quiescence, growth and stability, creation and destruction. As we contemplate these vast timescales, it's worth remembering that time itself is not absolute. Near a black hole, time slows down relative to the rest of the universe. If you could hover just outside the event horizon of Sagittarius A, millions of years would pass in the outside universe, while only minutes passed for you. This time, dilation, predicted by Einstein and confirmed by observation, adds another layer of mystery to our story. It means that from the black hole's perspective, if it could have a perspective, the universe is aging incredibly quickly. Galaxies are evolving in fast forward, stars are born and die in moments, civilizations rise and fall in the blink of an eye. Meanwhile, from our perspective, the black hole seems almost frozen, changing so slowly that we need generations of observations to notice any evolution at all. This relativity of time, this flexibility of space-time itself, is part of what makes black holes so fascinating. They're not just massive objects. They're regions where the fundamental nature of reality is different from what we experience in our daily lives. They're cosmic laboratories where the most extreme predictions of our physical theories are put to the test. And remarkably, so far these theories have held up. General relativity, formulated by Einstein over a century ago, accurately predicts the orbits of stars around Sagittarius A. Quantum mechanics, developed in the early 20th century, helps us understand the radiation from accretion disks. The standard model of particle physics explains the high-energy processes in black hole jets. These theories, developed to explain much simpler phenomena, work even in the extreme environment near a supermassive black hole. This success of our theories gives us confidence that we're on the right track in understanding these cosmic giants. But it also raises new questions. What happens at the singularity, the point of infinite density at the center of a black hole? How does quantum mechanics reconcile with general relativity in these extreme conditions? Is information destroyed when it falls into a black hole, or is it somehow preserved? These questions push the boundaries of our current understanding, pointing toward new physics we haven't yet discovered. As we drift deeper into this cosmic mystery, let's also consider the variety of galaxies and their central black holes. Not all galaxies are like the Milky Way. There are elliptical galaxies, massive spheroidal collections of old stars with little gas or dust. There are irregular galaxies, chaotic collections of stars and gas without clear structure. There are dwarf galaxies, tiny compared to giants like the Milky Way, but still containing millions or billions of stars. And remarkably, most of these galaxies, regardless of their type or size, seem to have central black holes. The relationship between black hole mass and galaxy properties holds across this entire range. It's as if nature has one recipe for making galaxies, and a supermassive black hole is an essential ingredient. But there are exceptions, and these exceptions are just as informative as the rule. Some dwarf galaxies don't seem to have central black holes, or if they do, they're too small for us to detect with current technology. Some galaxies might have binary black holes at their centers, two giants orbiting each other in a cosmic dance. Some might have intermediate mass black holes, filling the gap between stellar mass and supermassive black holes. Each of these exceptions tells us something about how galaxies and black holes form and evolve. They're like variations on a theme, helping us understand what's essential and what's variable in the cosmic recipe for galaxy formation. And as our instruments improve, as we peer deeper into space and further back in time, we're finding more of these exceptions, enriching our understanding of the cosmic ecosystem. The search for intermediate mass black holes is particularly intriguing. These would be black holes with masses between hundreds and hundreds of thousands of times the mass of our Sun, filling the gap between stellar mass and supermassive black holes. Finding them would help us understand how supermassive black holes form. Do they start small and grow, or do they form massive from the beginning? The answer might be both, with different formation channels operating under different conditions. Some scientists think intermediate mass black holes might lurk in globular clusters, dense collections of stars that orbit galaxies like satellites. Others might be wandering through galaxies, remnants of smaller galaxies that were absorbed by larger ones. Finding and studying these objects is one of the frontiers of modern astronomy, requiring clever observational strategies and sophisticated analysis techniques. As we explore these ideas drifting through the cosmic dark, remember that we're not just passive observers of this cosmic drama, we're participants. The elements in our bodies, the energy that powers our thoughts, the very space we occupy, all of it is connected to the story of galaxies and their central black holes. We're made of matter that has been processed through stars, scattered by supernova, gathered by gravity, and organized into the complex patterns we call life. And this process continues. Right now, as you listen to these words, new stars are being born in the Milky Way. Some of them will eventually die and contribute their elements to future generations of stars and planets. Sagittarius A continues its patient vigil at the center of our galaxy, its gravity helping to maintain the stable environment that allows us to exist and wonder about our place in the universe. In about 4 billion years, our galaxy will begin to merge with Andromeda, our nearest large galactic neighbor. This merger will take hundreds of millions of years to complete, a slow-motion collision that will reshape both galaxies. The supermassive black holes at the centers of both galaxies will eventually find each other, spiraling together and merging in an event that will send gravitational waves rippling across the universe. But this future merger isn't something to fear. Galaxies are mostly empty space, remember? The chance of our sun colliding with another star is vanishingly small. Instead, the merger will likely trigger new rounds of star formation, creating stellar nurseries where new suns and perhaps new worlds will be born. It will be a transformation, not a destruction, another chapter in the ongoing story of our cosmic neighborhood. This long-term perspective, this view of cosmic evolution over billions of years, can be both humbling and inspiring. We exist in a brief moment of cosmic time, a flash of consciousness in a universe that existed long before us and will exist long after. But in this moment, we have the remarkable ability to understand our context, to piece together the history of the cosmos, to predict its future, to find meaning in the vast cycles of creation and destruction that surround us. The question of why every galaxy has a supermassive black hole at its center touches on fundamental issues in cosmology. It's about understanding how structure forms in the universe, how gravity and other forces shape the cosmos, how complexity emerges from simplicity. These aren't just abstract scientific questions, they're about understanding our cosmic heritage, our place in the grand scheme of things. Consider this. The universe started in a hot, dense state about 13.8 billion years ago. At first, it was nearly uniform with only tiny fluctuations in density. Over billions of years, gravity amplified these fluctuations, pulling matter together to form the first stars and galaxies. Dark matter, invisible and mysterious, provided the scaffolding on which normal matter could accumulate, and somewhere in this process, supermassive black holes formed and took their places at the centers of galaxies. But the details of this process are still being worked out. Did black holes form first and then galaxies assembled around them? Did galaxies form first and then create their central black holes? Or did they form together, co-evolving from the very beginning? The answer might be different for different galaxies, or it might have changed over cosmic time. What we do know is that by the time the universe was 1 billion years old, supermassive black holes already existed. We see them as quasars, shining beacons in the early universe. Some of these early black holes were already billions of times the mass of our Sun. How they grew so massive so quickly is one of the great puzzles in astronomy. One possibility is that the first stars were much more massive than stars today. In the early universe, before heavy elements existed, gas clouds might have been able to collapse into stars hundreds or even thousands of times the mass of our Sun. When these monsters died, they would have left behind black holes far more massive than anything created by modern stars. These could have been the seeds that grew into supermassive black holes. Another possibility is direct collapse. Under the right conditions, a massive cloud of gas might collapse directly into a black hole without ever forming stars. This would create a black hole seed tens of thousands of times the mass of our Sun, giving it a head start in growing to supermassive size. This process would require special conditions, perhaps only possible in the early universe, but it could explain how supermassive black holes grew so quickly. Or perhaps both processes operated, creating a population of black hole seeds with a range of masses. These seeds would then grow by consuming gas and merging with other black holes, eventually reaching the supermassive sizes we observe today. The diversity of galaxies and their black holes might reflect this diversity of formation channels. As we contemplate these possibilities, floating in the darkness between certainty and mystery, it's worth appreciating how much we've learned and how much remains unknown. Every answer raises new questions. Every discovery opens new frontiers. This is the beauty of science, the endless journey of exploration and understanding. The tools we use to study supermassive black holes are marvels of human ingenuity. The Event Horizon Telescope, which gave us our first direct images of black hole shadows, combines data from telescopes around the world to create a virtual telescope the size of Earth. The Laser Interferometer. Gravitational Wave Observatory, or LIGO, can detect ripples in space-time smaller than the width of a proton. The James Webb Space Telescope can see galaxies as they were when the universe was just a few 100 million years old. Each of these instruments extends our senses in different ways, allowing us to perceive aspects of the universe that would otherwise be completely hidden from us. We can see the invisible, hear the unhearable, detect the undetectable. It's as if we've developed new senses, new ways of experiencing the cosmos, and what these new senses reveal is a universe far stranger and more wonderful than we ever imagined. Black holes that bend space and time, galaxies that collide and merge over millions of years, jets of particles moving at nearly the speed of light, gravitational waves that stretch and compress space itself. It's a cosmos that challenges our intuition, that forces us to think in new ways, that constantly surprises us with its beauty and complexity. As we near the end of this first part of our journey, let's take a moment to appreciate where we are. We've explored the discovery of supermassive black holes, their relationship with galaxies, the mysteries of their formation, and the tools we use to study them. We've considered our own place in this cosmic story, connected to Sagittarius AI through billions of years of cosmic evolution. But this is just the beginning. There's so much more to explore, so many more mysteries to contemplate. How do we actually observe these invisible giants? What evidence do we have for their existence? How do they affect their galaxies over cosmic time? These are questions we'll explore as we continue our journey through the cosmic night. For now, let yourself rest in the wonder of what we've discovered so far. Every galaxy has a dark heart, a supermassive black hole that has been there for most of cosmic history. These aren't monsters to be feared, but fundamental components of the cosmic architecture, as essential to galaxies as foundations are to buildings. They're part of the story of how the universe builds complexity, how it creates the conditions for stars, planets, and perhaps life itself. As you drift deeper into rest, carried by these thoughts of cosmic scale and deep time, remember that you're part of this story. The atoms in your body have orbited around Sagittarius A for billions of years. You're connected to the cosmos not just poetically but physically, through chains of cause and effect that stretch back to the beginning of time. And in this moment, in the quiet darkness, you're continuing that cosmic journey, a conscious part of the universe contemplating itself, wondering about its own nature, seeking to understand the mysterious relationship between galaxies and their dark hearts. It's a beautiful thing, this capacity for wonder, this ability to ask questions that span billions of light years and billions of years. The quiet question at the heart of every galaxy whispers to us across the vast expanses of space, and tonight we're ready to listen more closely. It's a question that many doubt we can answer definitively, but maybe we can cradle it gently in our minds, turning it over like a smooth stone worn by cosmic tides. Why does every galaxy seem to keep a supermassive black hole at its center? What if, just maybe, that dark heart is not an exception, but a pattern that whispers through the cosmos, written into the very fabric of how galaxies come to be? As we settle deeper into this exploration, let your mind drift with me to the center of our own galaxy, where something extraordinary is happening right now even as you listen to these words. Stars are dancing. Not the slow, stately waltz of our sun around the galactic center, which takes over 200 million years to complete, but a frantic, energetic dance of stars very close to Sagittarius A, moving at speeds that seem impossible until you realize what they're dancing around. Picture this with me. There's a star called S2, discovered by astronomers watching the galactic center with infrared telescopes that can peer through the cosmic dust. S2 is a blue giant, much more massive and luminous than our Sun, and it orbits Sagittarius A once every 16 years. 16 years! This star, which is several times more massive than our Sun, completes an entire orbit in less time than it takes Neptune to go once around our Sun, and at its closest approach, S2 is moving at nearly 3% of the speed of light, over 5,000 kilometers per second. But S2 isn't alone in its cosmic dance. There's S62, which whips around the black hole every 9.5 years, reaching speeds of nearly 7% of the speed of light at its closest approach. There's S47 moving so fast that if it were travelling in a straight line, it could cross the entire diameter of Earth's orbit around the Sun in less than 2 hours. These stars are part of what astronomers call the S-star cluster, a group of young, bright stars that orbit incredibly close to Sagittarius A, their paths traced out over years of patient observation. And yet, we keep our wonder gentle, exploring how these stars move, how their light delays and redshifts, how the center's gravity leaves soft fingerprints on everything around it. When we watch these stars, we're not seeing them in real time. The light from the galactic center takes 26,000 years to reach us, so we're watching a dance that happened when our ancestors were painting animals on cave walls, when mammoths still walked the earth. But the dance continues, unchanging in its fundamental patterns, following laws of physics that work the same way everywhere in the universe. The precision of these stellar orbits tells us something profound about the object they're orbiting. Only something incredibly massive and incredibly compact could cause stars to move this way. We can calculate the mass needed to hold these stars in their orbits, and the answer is always the same: 4 million times the mass of our Sun. But here's what makes it even more convincing. All of that mass must be contained within a region smaller than the orbit of S2 at its closest approach. That's a space smaller than our solar system, containing 4 million suns worth of mass. What else could it be but a black hole? Scientists have considered every alternative. Could it be a cluster of dark objects like neutron stars or stellar mass black holes? The problem is that such a cluster would be unstable. The objects would either merge together or fling each other out into space. Could it be some exotic form of matter we don't understand? Perhaps, but it would have to be something that doesn't emit any light, doesn't interact with normal matter except through gravity, and can remain stable while being incredibly dense. At some point, Occam's razor applies. The simplest explanation that fits all the observations is a supermassive black hole. We imagine together not a frightening answer, but a contemplative one that might reveal a quiet order in the way galaxies grow. Think about how a galaxy forms. It starts with a vast cloud of gas, mostly hydrogen and helium from the Big Bang, with a small seasoning of heavier elements from the first generation of stars. This cloud is not uniform, it has regions of slightly higher density, places where gravity is just a little bit stronger. Over millions of years, these denser regions pull in more matter, growing larger and denser still. As the gas falls inward, it heats up and starts to glow. If the conditions are right, the gas fragments into smaller clouds that collapse to form stars. But what happens at the very center, where the density is highest? Where all the infalling matter converges? Perhaps this is where the seed of a supermassive black hole is planted, growing along with the galaxy around it, feeding on the same reservoir of gas that forms the stars. This coevolution, this synchronized growth of galaxies and their central black holes, might explain the remarkable correlations we observe. The mass of the black hole correlates not just with the mass of the galactic bulge, but also with the velocity dispersion of stars in that bulge. In other words, the faster stars are moving in random directions in the center of a galaxy, the more massive its central black hole tends to be. This isn't a loose correlation with lots of scatter, it's a tight relationship that holds across different types of galaxies, across different masses, across billions of years of cosmic time. But how does the black hole know about the stars around it? How do the stars know about the black hole? They're separated by thousands of light years, far too distant to directly feel each other's gravity. The answer might lie in the process of galaxy formation itself, in the feedback between the black hole and its environment. When a black hole feeds, it releases energy. This energy heats the surrounding gas, can blow it out of the galaxy entirely, and can shut down star formation. When star formation stops, less gas falls toward the center, and the black hole's growth slows. It's a self-regulating system, a cosmic thermostat that keeps the black hole and galaxy in balance. Consider the possibility that this balance is not accidental but inevitable, arising from the fundamental physics of how matter behaves under gravity. Just as rivers flow to the sea, perhaps matter in a forming galaxy naturally flows toward the center, creating conditions that inevitably lead to a supermassive black hole. The specific mass of the black hole might depend on the details of the galaxy's formation history, but the presence of a black hole might be as natural and unavoidable as the formation of stars themselves. Scientists have observed this process happening in distant galaxies, catching them in the act of growing their central black holes. These active galactic nuclei, or AGN, shine across the electromagnetic spectrum as matter falls toward the black hole, heating up to millions of degrees and radiating energy. Some AGN are so bright they outshine their entire host galaxy, visible from billions of light-years away. These are the quasars, the quasi-stellar objects that puzzled astronomers when they were first discovered in the 1960s. But not all AGN are so dramatic. Some are more subtle, revealing themselves only through careful spectroscopic observations. The galaxy NGC 4258, for example, has water mesas orbiting its central black hole. These are clouds of water molecules that amplify microwave radiation like a natural laser. By tracking these mesas with radio telescopes, astronomers can map out the rotation of the disk around the black hole with exquisite precision, measuring the black hole's mass to within a few percent. In the galaxy M87, home to one of the most massive black holes we know of at 6.5 billion solar masses, we can actually see the jet launched by the black hole. This jet, a stream of particles moving at nearly the speed of light, extends for thousands of light-years, far beyond the galaxy itself. The energy carried by this jet is enormous, enough to affect the evolution of not just M87 but the entire cluster of galaxies it inhabits. And yet, in the silence between stars, these findings feel less like proofs and more like gentle lanterns lighting a path we can follow unhurried. Each observation adds another piece to the puzzle, another note to the cosmic symphony. We're not racing to solve everything immediately. We're taking our time, savouring each discovery, each new insight into how the universe works. The technology that allows us to make these observations is itself a marvel. The Very Large Telescope in Chile uses adaptive optics to correct for the blurring effects of Earth's atmosphere, achieving resolution comparable to space telescopes. The Atacama Large Millimeter Array, or ALMA, combines signals from dozens of radio dishes to create images of gas and dust around black holes. The Hubble Space Telescope, after more than 3 decades in orbit, continues to provide stunning images and spectra of galaxies near and far. Each of these instruments has its own story, its own contribution to our understanding. The Keck telescopes in Hawaii, with their segmented mirrors and adaptive optics, have tracked individual stars around Sagittarius A for decades. The Chandra X-ray Observatory reveals the hot gas falling into black holes and being blown out in winds. The Spitzer Space Telescope, before its retirement, showed us galaxies hidden behind veils of dust, their central black holes betrayed by infrared emission. But perhaps the most remarkable achievement in black hole observation came in 2019, when the Event Horizon Telescope collaboration released the first image of a black hole's shadow. This wasn't a photograph in the traditional sense. It was a reconstruction based on radio waves collected by telescopes around the world, combined using a technique called very long baseline interferometry. The result was an image of the supermassive black hole in M87, showing a bright ring of emission around a dark shadow, exactly as predicted by Einstein's general relativity. The image was both confirmation and revelation. Confirmation that black holes really do exist, that they really do bend light around them, creating a shadow, that our theories of gravity work even in these extreme conditions. But it was also a revelation of just how far we've come in our ability to observe the universe. We've gone from not even knowing other galaxies existed to imaging the event horizon of a black hole 55 million light-years away. Following that success in 2022, the Event Horizon Telescope collaboration released an image of our own black hole, Sagittarius A. This was in many ways more challenging than imaging M87's black hole despite being much closer. Sagittarius A is smaller and more variable, changing on timescales of minutes rather than days. It's like trying to photograph a puppy that won't sit still compared to photographing a sleeping cat. But the team succeeded, showing us the face of the dark heart of our own galaxy. These images are more than just pretty pictures or scientific achievements. They're proof that we can study objects that by their very nature cannot be seen directly. We can trace the invisible through its effects on the visible, map the unseeable through the distortions it creates in space and time. It's a kind of cosmic archaeology, piecing together the nature of black holes from the clues they leave in their surroundings. And what these clues tell us is that supermassive black holes are not anomalies, but standard features of galaxies. When we look at nearby galaxies whose centers we can study in detail, we almost always find evidence for a central massive object. Sometimes it's the orbital motion of stars, like in our own galaxy. Sometimes it's the rotation of gas disks, like in NGC 4258. Sometimes it's the presence of jets or other signs of AGN activity. But the evidence is there, written in light and motion and gravity. The question then becomes not whether galaxies have central black holes, but why. What is it about the process of galaxy formation that makes these objects inevitable? To understand this, we need to think about the early universe, about the conditions that existed when the first galaxies were forming. In the beginning, the universe was hot and dense, filled with a nearly uniform soup of particles and radiation. But there were tiny fluctuations, regions where the density was slightly higher or lower than average. These fluctuations, imprinted perhaps during cosmic inflation in the first fraction of a second after the Big Bang, were the seeds of all structure we see today. As the universe expanded and cooled, gravity began to amplify these fluctuations. Denser regions pulled in more matter, becoming denser still. This process, called gravitational instability, is the fundamental mechanism by which structure forms in the universe. It created the first stars, the first galaxies, the first clusters of galaxies, and perhaps, inevitably, it created the first black holes. But the story is more complex than simple gravitational collapse. Dark matter, that mysterious substance that makes up most of the matter in the universe, played a crucial role. Dark matter doesn't interact with light, doesn't form stars, doesn't heat up and radiate energy away. It just clumps under gravity, forming what astronomers call dark matter halos. These halos provided the gravitational wells into which normal matter could fall, the scaffolding on which galaxies could form. In the centers of these dark matter halos, where the density was highest, conditions might have been just right for forming massive black holes. The gas falling in would have been heated by compression and by the energy released from the first stars. This hot gas would have had trouble fragmenting into stars, perhaps instead flowing directly to the center, where it could form a massive black hole seed. Or perhaps the first stars themselves were the key. In the early universe, before heavy elements existed to help gas cool and fragment, stars might have been much more massive than they are today. These population 3 stars, as astronomers call them, could have been hundreds or even thousands of times the mass of our Sun. When they died, they would have left behind black holes far more massive than anything formed by modern stars. These black hole seeds, however they formed, would then grow by accretion and mergers. Gas falling into the black hole would heat up and radiate, but not all the energy would escape. Some would go into accelerating particles in jets, some into heating the surrounding gas, some into radiation pressure that pushes gas away. This feedback would regulate the growth of the black hole, creating the correlations we observe between black hole mass and galaxy properties. The process would have been messy and chaotic, with periods of rapid growth alternating with periods of quiescence. Sometimes the black hole would be fed by smooth flows of gas from the intergalactic medium. Sometimes it would feast on gas delivered by galaxy mergers. Sometimes it would go hungry, sitting quietly while the galaxy around it evolved. This feast or famine scenario might explain why we see such a range of AGN activity in the universe today. Some galaxies have incredibly luminous quasars at their centers, shining with the light of trillions of suns. Others have low luminosity AGN, barely visible above the stellar background. And many, like our own Milky Way, have quiet black holes, not currently accreting significant amounts of matter. The duty cycle of AGN activity, the fraction of time a black hole spends in an active state, is still not well understood. Observations suggest that the most luminous quasars are rare and short-lived, lasting perhaps only millions of years, but lower levels of activity might be more common and longer-lasting. Over the lifetime of a galaxy, its central black hole might go through many cycles of activity and quiescence, like a cosmic heartbeat with a very slow rhythm. This variability adds another layer of complexity to our story. When we observe a galaxy, we're seeing it at one moment in its history. Its black hole might be active or quiet, growing or static. To understand the full relationship between galaxies and their black holes, we need to observe many galaxies at different stages of evolution, piecing together the complete picture from these snapshots. Fortunately, the universe provides us with a natural time machine. When we look at distant galaxies, we're seeing them as they were in the past. Light from a galaxy a billion light-years away shows us that galaxy as it was a billion years ago. By observing galaxies at different distances, we can see how the population of galaxies and their black holes has evolved over cosmic time. What we find is remarkable. In the early universe, when galaxies were younger and more gas-rich, black holes were more active. The peak of quasar activity was around 10 billion years ago, when the universe was only a few billion years old. Since then, the average activity level has declined. Galaxies have used up much of their gas-forming stars, leaving less to feed their central black holes. The universe as a whole is settling down, becoming more quiescent with age. But this doesn't mean the story is over. Galaxies continue to evolve, continue to interact with their environments. Our own Milky Way will merge with Andromeda in about 4 billion years, an event that might reawaken both galaxies' central black holes. Other galaxies are experiencing mergers right now, their black holes growing and shining as they feast on the inflowing gas. And in the far future, when the universe is much older and colder than it is today, black holes might be the only remaining sources of energy. As stars burn out and galaxies fade, black holes will persist, slowly evaporating through Hawking radiation, but lasting for unimaginable lengths of time. The largest supermassive black holes will be the last objects to evaporate, finally disappearing in a burst of radiation after something like 10-100 years, a number so large it defies comprehension. But let's not get lost in these vast timescales. Let's return to the present, to what we can observe and understand today. The evidence for supermassive black holes in galactic centers is overwhelming. We see their gravitational influence on stars and gas. We detect the radiation from matter falling into them. We observe the jets they launch and the winds they drive. We've even imaged their shadows, seen the way they bend light around themselves. Each piece of evidence reinforces the same conclusion. Galaxies and their central black holes are intimately connected, their histories intertwined, their futures linked. The black hole is not an interloper or a parasite, but an integral part of the galactic ecosystem, as essential as the stars and gas and dark matter that make up the rest of the galaxy. This relationship extends beyond individual galaxies to the larger structures of the universe. Galaxy clusters, collections of hundreds or thousands of galaxies bound together by gravity, are affected by the AGN in their member galaxies. The jets and winds from these AGN heat the intracluster medium, the hot gas that fills the space between galaxies. This heating can prevent the gas from cooling and forming new galaxies, affecting the evolution of the entire cluster. The most massive black holes tend to be found in the most massive galaxies, which tend to be at the centers of galaxy clusters. These black holes, despite being tiny compared to their host clusters, can influence regions millions of light years across. It's another example of how black holes punch above their weight, how their influence extends far beyond what their size would suggest. As we continue to explore this cosmic mystery, new questions arise. How do black holes affect the formation of stars in their galaxies? Do they trigger star formation by compressing gas, or do they suppress it by heating or removing gas? The answer seems to be both, depending on the circumstances. Near the black hole, star formation is generally suppressed, but farther out, the compression of gas by AGN-driven winds might actually trigger the formation of new stars. This complex interplay between creation and destruction, between heating and cooling, between inflow and outflow, is what makes the study of galaxies and their black holes so fascinating. There's no simple story, no single mechanism that explains everything. Instead, we have a rich tapestry of processes operating on different scales, at different times, in different environments. The role of magnetic fields adds another layer of complexity. The gas falling toward a black hole carries magnetic fields with it, and these fields can become incredibly strong near the event horizon. They can channel the flow of matter, launch jets, and even extract energy from the black hole's rotation. The details of how this works are still being worked out, requiring sophisticated computer simulations and observations across the electromagnetic spectrum. The spin of the black hole itself is another important factor. A rotating black hole, what physicists call a Kerr black hole, has different properties than a non-rotating one. It can extract energy from infalling matter more efficiently, launch more powerful jets, and affect its surroundings in different ways. Measuring black hole spin is challenging, but astronomers have developed several techniques based on X-ray observations and the modelling of accretion disks. Some black holes appear to be spinning at nearly the maximum rate allowed by general relativity, where the event horizon is rotating at close to the speed of light. Others spin more slowly, perhaps because they've been fed by chaotic accretion that doesn't have a consistent direction. The spin of a black hole contains information about its formation and growth history, another piece of the puzzle we're trying to solve. As our observations improve and our theoretical understanding deepens, we're beginning to see patterns within patterns. Not only do all galaxies seem to have central black holes, but the properties of these black holes correlate with the properties of their galaxies in specific ways. These correlations, these scaling relations as astronomers call them, are clues to the underlying physics that governs galaxy and black hole evolution. The M-sigma relation, the correlation between black hole mass and stellar velocity dispersion, is perhaps the most famous of these, but there are others. The mass of the black hole correlates with the luminosity of the galactic bulge, with the mass of the dark matter halo, even with the number of globular clusters in the galaxy. Each correlation tells us something about how these systems formed and evolved together. But correlations don't necessarily imply causation. Just because two things are related doesn't mean one causes the other. They might both be caused by a third factor, or they might be connected through a complex web of feedback loops. Untangling these relationships, understanding not just what correlates with what, but why, is one of the major challenges in modern astrophysics. This is where theory and simulation come in. By building computer models of galaxy formation, including all the physics we think is important, astronomers can test different scenarios and see which ones reproduce the observations. These simulations have become incredibly sophisticated, tracking the evolution of billions of particles over billions of years, including gravity, hydrodynamics, star formation, black hole growth, and feedback. The results of these simulations are encouraging. They can reproduce many of the observed properties of galaxies and their black holes, including the scaling relations we've been discussing, but they also make predictions suggesting new observations that could test our understanding. This interplay between theory, simulation, and observation is how science progresses, each approach informing and constraining the others. As we float through this cosmic contemplation, consider how remarkable it is that we can even attempt to understand these things. The relationship between galaxies and their central black holes plays out over billions of years and billions of light years, scales so vast they dwarf human experience. Yet with patience, ingenuity, and collaboration, we're piecing together the story, one observation, one calculation, one insight at a time. The instruments we use to study distant galaxies and their black holes are triumphs of human engineering. The James Webb Space Telescope, launched in 2021, can see galaxies as they were when the universe was just a few 100 million years old. It's showing us baby galaxies, still in the process of forming, some perhaps assembling their first central black holes. These observations are helping us understand how the galaxy-black hole relationship was established in the first place. ALMA, the Atacama Large Millimeter Submillimeter Array, reveals the cold gas and dust that feeds black holes and forms stars. By observing at wavelengths invisible to our eyes, ALMA shows us aspects of galaxies we couldn't see any other way. It's particularly good at studying high redshift galaxies, those in the early universe, where much of the optical light has been shifted into the infrared and submillimeter. Future instruments promise even more revelations. The extremely large telescope under construction in Chile will have a mirror nearly 40 meters across, larger than any optical telescope ever built. It will be able to study the centers of nearby galaxies in unprecedented detail, perhaps directly detecting intermediate mass black holes that have so far eluded us. The Square Kilometre Array, a radio telescope being built in South Africa and Australia, will be sensitive enough to detect the faint radio emission from ordinary galaxies at high redshift. It might reveal a population of black holes we haven't seen before, those that are growing slowly and steadily rather than in dramatic bursts. And then there's the Laser Interferometer Space Antenna, or LISA, planned for launch in the 2030s. LISA will detect gravitational waves from merging supermassive black holes, actually hearing the ripples in spacetime as these giants come together. This will open an entirely new window on black hole physics, allowing us to study processes we can't observe any other way. Each of these instruments extends our reach, our ability to perceive and understand the universe. They're like new senses revealing aspects of reality that were previously hidden. And with each new observation, each new discovery, the picture becomes clearer, the story more complete. But even as we celebrate these achievements, we must remember how much we don't know. We still don't fully understand how supermassive black holes form. We don't know exactly how they affect their galaxies or how their galaxies affect them. We don't know if there are galaxies without central black holes or black holes without galaxies. We don't know what happens to information that falls into a black hole or how black holes will ultimately evaporate. These unknowns are not failures but opportunities. They're the questions that will drive the next generation of astronomers, the mysteries that will inspire new instruments, new theories, new ways of thinking about the universe. Science is not about having all the answers, but about asking better questions, and the relationship between galaxies and their central black holes provides some of the best questions we have. As we drift through these ideas, let them settle gently in your mind like sediment in still water. There's no need to grasp everything firmly, to hold every detail. Let the concepts flow through your consciousness, leaving traces, patterns, connections. Understanding often comes not through intense focus, but through relaxed contemplation, through allowing ideas to percolate and combine in unexpected ways. The universe reveals itself slowly, patiently, to those who take the time to look and listen. The relationship between galaxies and their black holes has been developing for billions of years. We can take our time understanding it, appreciating not just the destination, but the journey of discovery itself. Scientists have observed stars whirling around an invisible mass at the center of our own Milky Way, tracing smooth loops that reveal Sagittarius A with calm clarity. These observations didn't happen overnight. They represent decades of patient watching, of developing new technologies, of refining techniques. The astronomers who first began tracking these stars couldn't have imagined the precision we achieve today, just as we can't fully imagine what future astronomers will accomplish. The story of Andrea Ghez and Reinhard Genzel, who shared the Nobel Prize for their observations of Sagittarius A, is particularly inspiring. Working independently with different telescopes on different continents, they both tracked stars around the galactic center for years, gradually building up the evidence for a supermassive black hole. Their persistence, their dedication to careful observation over decades, exemplifies the patience required to understand the universe. But they didn't work alone. Behind every major discovery are teams of people, graduate students analyzing data late into the night, engineers maintaining and improving telescopes, theorists developing models to interpret observations, administrators securing funding and telescope time. Science, especially astronomy, is a collective endeavor, a collaboration not just across institutions and countries but across generations. The data from these observations is now public, available to anyone with an internet connection. A student in a remote village can download the same data that led to a Nobel Prize, can trace the orbits of stars around Sagittarius A, can participate in the process of discovery. This democratization of data, this opening of astronomy to the world, is one of the beautiful developments of our time. And it's not just professional astronomers who contribute. Amateur astronomers, with increasingly sophisticated equipment, discover supernovae in distant galaxies, monitor AGN variability, contribute to our understanding of the universe. Citizen science projects allow anyone to help classify galaxies, search for gravitational lenses, identify interesting objects for professional follow-up. We're all part of this quest to understand our cosmic context. Data from the Event Horizon Telescope, with help from ALMA, has revealed the soft shadow of M87, a ring of light around a patient darkness. This image, which made headlines around the world, represents not just a scientific achievement, but a human one. It shows what we can accomplish when we work together, when we combine our resources and expertise toward a common goal. The image itself is beautiful in its simplicity, a bright ring surrounding a dark shadow, exactly as Einstein's theory predicted. But behind that simplicity lies incredible complexity. The physics of curved space-time, the behavior of plasma in extreme magnetic fields, the propagation of radio waves across intergalactic space, the mathematics of interferometry and image reconstruction. Each pixel in that image represents countless hours of work, countless calculations, countless decisions about how to process and interpret the data. And yet, the image also raises new questions. Why is the ring brighter on one side than the other? How stable is the structure over time? What can we learn about the black hole's spin and the properties of the accretion flow? Each answer leads to new questions, each discovery to new mysteries. This is the nature of science, always pushing forward, always expanding the frontier of knowledge. Radio masers and careful stellar motions, from instruments like Keck, the VLT and Gaia, whisper distances and speeds that fit the presence of immense compact centers. These observations use different techniques, different wavelengths, different physical principles, yet they all point to the same conclusion. This convergence of evidence, this consistency across different methods, is what gives us confidence in our understanding. The Gaia spacecraft, mapping the positions and motions of over 1 billion stars in our galaxy, is revolutionizing our understanding of the Milky Way. While it can't peer through the dust to see the galactic center directly, it's mapping the overall structure of our galaxy with unprecedented precision. This includes detecting the subtle influences of Sagittarius A on the galaxy as a whole, the way its gravity affects stellar orbits even thousands of light-years away. The Very Large Telescope in Chile, with its adaptive optics system that corrects for atmospheric blurring, can track individual stars near Sagittarius A with remarkable precision. Night after night, year after year, astronomers use this instrument to monitor the galactic center, building up an ever more detailed picture of the stellar dynamics around our galaxy's central black hole. The Keck telescopes in Hawaii, with their own adaptive optics systems, provide complementary observations from the Northern Hemisphere. The combination of data from multiple telescopes, multiple locations, multiple times, creates a robust data set that can reveal subtle effects, test theoretical predictions, and potentially discover new phenomena we haven't anticipated. And yet, in the silence between stars, these findings feel less like proofs, and are more like gentle lanterns lighting a path we can follow, unhurried. Each observation is a step forward, but we're not racing to a finish line. We're exploring, wandering through the cosmic landscape, pausing to admire particularly beautiful views, sometimes backtracking when we realize we've misunderstood something. This patient approach to understanding is perhaps best exemplified by the study of AGN variability. Some active galactic nuclei change their brightness on timescales of hours or days, others over years or decades. To understand these variations, astronomers need to observe the same objects repeatedly over long periods. This requires dedication, patience, and often international collaboration to ensure continuous coverage. The Sloan Digital Sky Survey, which has mapped millions of galaxies over the past 2 decades, provides a different kind of patience. By systematically surveying large areas of sky, measuring redshifts and taking spectra of countless galaxies, SDSS has built up a statistical picture of the galaxy population. This includes finding rare objects, outliers that might reveal new physics or challenge our current understanding. These large surveys are like censuses of the universe, cataloguing its contents and allowing us to see patterns that wouldn't be visible from individual observations. They've revealed that the correlation between black hole mass and galaxy properties holds not just for nearby galaxies but for distant ones as well, suggesting this relationship was established early and has been maintained over cosmic time. But surveys also reveal exceptions, galaxies that don't fit the pattern. Some galaxies seem to have undermassive black holes, others overmassive ones. Some might not have central black holes at all, or their black holes might be binary systems, 2 giants orbiting each other. These exceptions are not problems to be explained away, but opportunities to refine our understanding, to discover new aspects of galaxy evolution we hadn't considered. The search for binary supermassive black holes is particularly intriguing. When galaxies merge, their central black holes should eventually find each other and form a binary system. These binaries should spiral together and eventually merge, sending out gravitational waves that future detectors like LISA will be able to detect. But finding binary black holes in the act of spiraling together has proven challenging. Some candidates have been identified, galaxies with double nuclei or periodic variations that might indicate orbital motion, but confirming these as true binary black holes rather than chance projections or other phenomena requires careful observation and analysis. It's another example of how astronomy requires patience, how discoveries often take years or decades to confirm. The possibility of recoiling black holes adds another wrinkle to the story. When 2 black holes merge, the gravitational waves they emit can carry away momentum, giving the merged black hole a kick that can send it flying through or even out of its galaxy. Some galaxies might have off-center black holes, or might have lost their black holes entirely. Finding these recoiling black holes, if they exist, would provide crucial tests of our understanding of gravitational wave physics and galaxy evolution. As we contemplate these possibilities, drifting through scenarios and implications, remember that uncertainty is not weakness but honesty. Science progresses not by proclaiming absolute truths, but by gradually narrowing the range of possibilities, by becoming less wrong over time. Our current understanding of galaxies and their central black holes is undoubtedly incomplete, perhaps even wrong in some important ways. But it's less wrong than our understanding a decade ago, and that was less wrong than a decade before that. This gradual refinement, this slow convergence toward truth, is how science works. It's not dramatic or sudden, but patient and persistent, like water wearing away stone. Each observation, each calculation, each idea contributes to the erosion of ignorance, the gradual revealing of how the universe actually works. The discovery that galaxies have central black holes is part of a larger realization about the universe, that it's far more extreme, far more varied, far stranger than we ever imagined. Black holes themselves were once thought to be mathematical curiosities, solutions to Einstein's equations that surely couldn't exist in nature. Now we know they're everywhere, from stellar mass black holes scattered throughout galaxies to the supermassive giants at galactic centers. This progression from impossibility to ubiquity is common in science. Continental drift was once considered absurd. Now plate tectonics is the foundation of geology. The idea that time could run at different rates in different places seemed like fantasy. Now GPS satellites must account for relativistic time dilation to maintain accuracy. The universe consistently surprises us, reveals itself to be more interesting than our limited imaginations initially conceive. Perhaps this is why the night, with its invitation to expand, our thinking beyond daily concerns, is the perfect time to contemplate these cosmic mysteries. In the darkness, our minds are more open to possibility, more willing to accept the strange and wonderful. The same mental state that allows us to dream, allows us to imagine black holes, curved space-time, galaxies billions of light years away. As we explore these ideas together, you might notice your breathing has slowed, your muscles have relaxed, your mind has entered a state of calm receptivity. This is not coincidence but connection. The same physics that governs black holes governs our bodies. The same atoms that orbit Sagittarius A make up our cells. We're not separate from the cosmic story but part of it, temporary arrangements of matter and energy that have become conscious enough to contemplate our own origins. Observations suggest that bright quasars shine when the universe is still very young. JWST and Hubble show beacons in the early dawn. These cosmic lighthouses, powered by supermassive black holes feeding on surrounding gas, are some of the most distant objects we can see. When we observe a quasar 12 billion light-years away, we're seeing it as it was when the universe was less than 2 billion years old, a cosmic infant still learning to form galaxies and stars. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is pushing our observations even further back, finding galaxies and possibly quasars when the universe was just a few 100 million years old. These observations are challenging our understanding of how quickly structures can form, how rapidly black holes can grow. Some of these early galaxies seem too massive, their black holes too large, for our current models to easily explain. This tension between observation and theory is productive. It forces us to reconsider our assumptions, to develop new ideas, to refine our models. Perhaps black holes could grow faster than we thought under certain conditions. Perhaps they formed from more massive seeds than we assumed. Perhaps there are formation mechanisms we haven't considered. Each possibility opens new avenues of investigation, new predictions to test against observation. The Hubble Space Telescope, after more than 30 years of operation, continues to contribute to our understanding of distant galaxies and their black holes. Its deep fields, images where it stared at seemingly empty patches of sky for days, revealed thousands of previously unknown galaxies, some hosting active nuclei that betray the presence of growing black holes. These deep observations show us that the universe was more active in the past. The peak of star formation was about 10 billion years ago, the peak of quasar activity around the same time. Since then, both have been declining. The universe is settling down, becoming more sedate with age. Galaxies are running out of gas to form stars and feed their black holes. The wild days of youth are giving way to a calmer maturity. But this doesn't mean nothing interesting is happening now. Galaxy mergers still occur, triggering new rounds of star formation and black hole growth. Cooling flows in galaxy clusters can deliver fresh gas to central galaxies. Recycling of gas from stellar winds and supernovae provides raw material for new generations of stars. The universe is still evolving, just more slowly than in its youth. Consider this. Perhaps the first black hole seeds arise from the quiet end of the first stars, or from clouds that collapse directly, softly, without ever lighting a stellar flame. The first stars in the universe, formed from pristine hydrogen and helium without any heavy elements to help the gas cool, are thought to have been monsters. Some models suggest they could have been hundreds or even thousands of times the mass of our Sun. When these giants died, they wouldn't have exploded as normal supernovae. Instead, they might have collapsed directly into black holes, their cores too massive for any force to resist gravity's pull. These direct collapse black holes would have been born with masses of hundreds or thousands of solar masses, giving them a head start in growing to supermassive size. Alternatively, or perhaps additionally, massive gas clouds in the early universe might have collapsed directly into black holes without ever forming stars. This would require special conditions. The gas would need to be prevented from fragmenting into stars, perhaps by being kept hot by ultraviolet radiation from nearby galaxies. If such direct collapse occurred, it could create black hole seeds of 10,000 to 100,000 solar masses, massive enough to grow to supermassive size within the available time. ALMA maps cold gas that might feed these beginnings, and surveys like SDSS and PAN-STARRS trace where they may be. The Atacama Large Millimeter Submillimeter Array is particularly good at detecting the cold molecular gas that serves as fuel for both star formation and black hole growth. By mapping this gas in distant galaxies, ALMA helps us understand the raw material available for building galaxies and growing their central black holes. The Sloan Digital Sky Survey, with its systematic approach to mapping the universe, has catalogued millions of galaxies and hundreds of thousands of quasars. This vast database allows astronomers to study the evolution of galaxies and their black holes statistically, looking for patterns and correlations that wouldn't be visible from individual objects. PAN-STARRS, the Panoramic Survey Telescope and Rapid Response System, repeatedly images large areas of sky, looking for things that change or move. This includes finding new quasars, especially those that vary in brightness, which helps us understand how black holes feed and grow. What if, just maybe, both paths happen, many small seeds and a few rare heavy seeds, like different lullabies that still lead to sleep? This diversity of formation mechanisms might explain the diversity we see in galaxies and their black holes today. Some black holes might have grown from stellar mass seeds through steady accretion and mergers. Others might have started as massive seeds from direct collapse, reaching supermassive size more quickly. The relative importance of these different channels might have varied with cosmic time and environment. In the densest regions of the early universe, direct collapse might have been more common. In less dense regions, growth from stellar seeds might have dominated. This environmental dependence could explain some of the scatter we see in the correlations between black holes and their galaxies. Understanding black hole seeds is crucial for understanding the subsequent evolution of galaxies. A galaxy that starts with a massive seed might evolve differently than one that starts with a smaller seed. The seed mass might affect when the black hole becomes active, how it interacts with its galaxy, and what final mass it achieves. Computer simulations are essential tools for exploring these different scenarios. By modelling the collapse of gas clouds, the formation of the first stars, and the growth of black holes, astronomers can test which combinations of processes reproduce the observed population of galaxies and quasars. These simulations require enormous computational resources, tracking the evolution of billions of particles over billions of years. The results of these simulations are encouraging but not definitive. They can produce galaxies and black holes with properties similar to those observed, but often require fine-tuning of parameters. This suggests we're on the right track but haven't yet captured all the relevant physics. Perhaps we're missing important feedback mechanisms, or perhaps our models of star formation or black hole accretion need refinement. One of the challenges in simulating black hole growth is the vast range of scales involved. The event horizon of a supermassive black hole is smaller than our solar system, but its influence extends across an entire galaxy. No simulation can capture this entire range with full detail, so approximations and subgrid models are necessary. Developing and testing these models is an active area of research, requiring close collaboration between theorists and observers. As we float through these possibilities, these different paths to creating the dark hearts of galaxies, notice how each scenario has its own beauty, its own elegance. The universe rarely does things in just one way. It prefers diversity, multiple solutions to the same problem, redundancy and richness. This multiplicity of mechanisms, this cosmic creativity, is part of what makes the universe so endlessly fascinating. The search for the first black holes, the seeds from which today's giants grew, is one of the frontiers of modern astronomy. These objects, if we can find them, would tell us about conditions in the early universe, about how structure first formed, about the processes that shape the cosmos we see today. They're cosmic fossils, preserving information about an era we can't observe directly. Some astronomers are searching for intermediate mass black holes in nearby dwarf galaxies, thinking these might be descendants of the first seeds that never grew to supermassive size. Others are looking for wandering black holes in galaxy halos, remnants of smaller galaxies that were absorbed without their black holes merging. Still others are searching for gravitational wave signals from merging intermediate mass black holes, which would provide direct evidence for this missing population. The discovery of gravitational waves by LIGO has opened an entirely new way to study black holes. While LIGO is sensitive to stellar mass black hole mergers, future detectors like LISA will be able to detect mergers of supermassive black holes. These observations will provide unprecedented insights into black hole physics, allowing us to test general relativity in the strong field regime and measure black hole masses and spins with exquisite precision. But LISA might also detect intermediate mass black hole mergers, potentially catching seed black holes in the act of growing. These observations could definitively answer questions about how supermassive black holes formed, whether from small seeds or large ones, whether through accretion or mergers. It's an exciting prospect, a new window on the universe that will open in the coming decades. As we anticipate these future discoveries, it's worth reflecting on how far we've come. A century ago, we didn't know galaxies existed beyond our own. Half a century ago, black holes were theoretical curiosities. A quarter century ago, we had only indirect evidence for supermassive black holes. Now we've imaged their shadows, measured their masses, traced their evolution across cosmic time. The pace of discovery is breathtaking, yet each answer reveals new questions, new depths to explore. This is the beauty of science, the endless frontier that recedes as we approach it. We'll never know everything, never run out of mysteries to investigate. The universe is too vast, too complex, too creative for any finite mind or even any finite civilization to fully comprehend. But the journey of trying to understand, of pushing the boundaries of knowledge, of satisfying our curiosity about our cosmic context, is itself the reward. As you continue to drift with these ideas, letting them settle into the quiet spaces of your mind, consider what it means to be part of this cosmic story. Every atom in your body except hydrogen was forged in a star. You're made of cosmic material, shaped by cosmic processes, participating in a cosmic evolution that connects you to everything else in the universe. The same physics that governs black holes governs your neurons. The same chemistry that occurs in stellar atmospheres occurs in your cells. This connection is not metaphorical but literal. You are the universe contemplating itself, a way for the cosmos to know itself. Your curiosity about black holes and galaxies is the universe's curiosity about its own nature. Your wonder at the cosmic mystery is the universe's wonder at itself. In a very real sense, you are not in the universe, you are the universe, a localized concentration of matter and energy that has become conscious. Accretion disks turn gravity into light, and yet the glow can be a whisper, steady, humming, serene. When matter falls toward a black hole, it doesn't just disappear into the darkness. It spirals inward, forming a disk that can be millions of degrees hot, radiating across the electromagnetic spectrum. But this process doesn't have to be violent or chaotic. Often it's gentle, a steady flow of matter creating a constant glow, like a cosmic candle flame that burns for millions of years. The physics of accretion disks is beautiful in its complexity. As matter spirals inward, it must lose angular momentum, which is transferred outward through the disk by viscosity and magnetic fields. This creates a temperature gradient, with the inner parts of the disk much hotter than the outer parts. The inner regions emit X-rays, the middle regions ultraviolet and optical light, the outer regions infrared. By observing at different wavelengths, astronomers can map out the structure of these disks, understanding how matter flows toward its final plunge into the black hole. But not all the matter that approaches a black hole falls in. Some is blown away by radiation pressure, the force exerted by light itself. When the disk is very luminous, this radiation pressure can exceed gravity, driving winds that carry matter away from the black hole and out of the galaxy. These winds can reach speeds of thousands of kilometers per second, carrying enormous amounts of energy and momentum. Scientists have observed a quiet pattern between the mass of a galaxy's central black hole and the way its stars drift and settle, suggesting a shared gentle growth. This correlation, known as the M-sigma relation, is remarkably tight. Measure the velocity dispersion of stars in a galaxy's bulge, and you can predict the mass of its central black hole to within a factor of 2 or 3. This might not sound very precise, but given that black holes range over many orders of magnitude in mass, this correlation is remarkably strong. What makes this correlation even more remarkable is that it holds for different types of galaxies. Elliptical galaxies, lenticular galaxies, and the bulges of spiral galaxies all follow the same relation. It's as if there's a universal recipe that determines the ratio of black hole mass to bulge properties, regardless of how the galaxy formed or evolved. But the correlation isn't perfect. There's scatter, galaxies that lie above or below the average relation. This scatter itself is informative. It might tell us about different formation histories, different merger histories, or different feedback mechanisms. Some galaxies might have grown their black holes faster than average, others slower. Understanding this scatter, what causes it and what it means, is an active area of research. The correlation extends beyond just velocity dispersion. Black hole mass also correlates with bulge luminosity, bulge mass, and even the number of globular clusters in a galaxy. Each of these correlations provides a different perspective on the connection between black holes and their galaxies, different clues to the underlying physics. Chandra reveals soft X-ray halos. ALMA listens for cool molecular gas. Hubble and JWST see dust lanes that feed the center like slow rivers. The Chandra X-ray Observatory, orbiting high above Earth's atmosphere, can detect the million-degree gas that surrounds active black holes. This hot gas, heated by compression and shocks, emits X-rays that Chandra can image with remarkable precision. These observations reveal not just the immediate environment of the black hole, but also the larger-scale effects of AGN feedback. ALMA, operating at millimeter and submillimeter wavelengths, sees the universe in a different light. It detects the emission from cold molecular gas, the raw material for star formation. By mapping this gas in galaxies near and far, ALMA shows us the fuel supply for both star formation and black hole growth. It can trace gas flowing toward galactic centers, feeding black holes, and gas being blown out by AGN winds, shutting down star formation. The Hubble Space Telescope, with its sharp optical and near-infrared vision, reveals the detailed structure of galaxies. It shows us dust lanes spiraling toward galactic centers, bars that funnel gas inward, rings of star formation triggered by AGN outflows. Each image is a snapshot of the ongoing interaction between galaxies and their central black holes. The James Webb Space Telescope, with its unprecedented infrared capabilities, is revolutionizing our view of distant galaxies. It can peer through cosmic dust to see hidden star formation and black hole activity. It's finding galaxies in the early universe that challenge our understanding. Massive galaxies that formed faster than our models predicted, possibly indicating that black holes played a different role in early galaxy formation than they do today. Perhaps feedback from the heart does not shout but guides, balancing starbirth and stillness so the galaxy can breathe, in and out across the ages. This gentle regulation, this cosmic thermostat, might be the key to understanding why galaxies look the way they do. Without AGN feedback, models predict that massive galaxies would have formed far more stars than we observe. The energy from the central black hole, even when it's relatively quiet, might be just enough to keep the gas in, the galaxy warm, preventing it from cooling and forming stars too rapidly. This balance between heating and cooling, between star formation and quiescence, plays out over millions and billions of years. It's not a steady state, but a dynamic equilibrium, with periods of activity and rest, growth and stability. The galaxy breathes, inhaling gas from its surroundings, exhaling winds driven by supernovae and AGN, in a rhythm set by the complex interplay of gravity, radiation, and magnetism. The role of AGN feedback in galaxy evolution is still being debated and refined. Some astronomers argue it's essential for explaining the properties of massive galaxies. Others suggest that stellar feedback alone might be sufficient. The truth probably lies somewhere in between, with both processes playing important roles at different times and in different types of galaxies. Computer simulations that include AGN feedback can reproduce many observed properties of galaxies, including their colours, sizes, and star formation rates. But these simulations require assumptions about how black holes accrete matter and how they couple their energy to the surrounding gas. Different assumptions lead to different results, and observations are needed to constrain these models. One of the challenges is that AGN feedback operates on a huge range of scales. Near the black hole, the energy comes out in radiation and fast winds. On galaxy scales, it might manifest as bubbles of hot gas or jets that heat the circumgalactic medium. On even larger scales, in galaxy clusters, AGN can affect the intracluster medium, preventing cooling flows that would otherwise fuel massive star formation. This multi-scale nature of AGN feedback makes it difficult to observe and model. No single observation can capture the entire process, and no simulation can resolve all the relevant scales. Instead, astronomers must piece together the picture from different observations at different wavelengths, different scales, different cosmic epochs. The discovery of Fermi bubbles extending above and below our galaxy's disk provided dramatic evidence for past AGN activity in the Milky Way. These enormous structures, visible in gamma rays, might be the remnants of an AGN outburst millions of years ago when Sagittarius A was more active. They remind us that even quiet black holes like our own have had more dramatic moments in their past. Similar bubbles and cavities are seen in other galaxies and in galaxy clusters, carved out by AGN jets and filled with hot diffuse gas. These structures can persist for millions of years, continuing to affect their surroundings long after the AGN has gone quiet. They're like cosmic fossils, preserving evidence of past activity and helping us understand the long-term effects of AGN feedback. The interplay between black holes and star formation is particularly complex near galactic centers. The strong gravitational field of the black hole creates tidal forces that can disrupt molecular clouds, preventing star formation. But the compression of gas in the accretion disk or in shocks driven by AGN outflows might trigger star formation in some regions. The result is a complex pattern of star formation and suppression that varies with distance from the black hole and with time. Observations of nearby galactic centers, where we can resolve individual stars and star clusters, show this complexity in detail. Young, massive stars orbit surprisingly close to supermassive black holes. Their formation a puzzle given the disruptive tidal forces. Older stars show a different distribution, perhaps reflecting different formation conditions in the past. Each population of stars tells part of the story of how galactic centers evolve. The discovery of hypervelocity stars, stars moving so fast they'll escape the galaxy entirely, provides another window on the extreme environment near supermassive black holes. These stars were likely part of binary systems that ventured too close to the black hole. The black hole captured one star and flung the other out at enormous speed, a cosmic slingshot that can accelerate stars to over 1,000 kilometers per second. These hypervelocity stars are messengers from the galactic center, carrying information about the population of stars near the black hole and the black hole's mass and spin. By tracking their trajectories backward, astronomers can learn about their origins and the violent event that sent them on their journey. They're another example of how black holes, despite being invisible themselves, leave traces of their presence throughout the galaxy. As we contemplate these gentle and not-so-gentle influences of black holes on their galaxies, let your mind wander through the possibilities. Perhaps in some galaxies the black hole is like a gardener, carefully tending the galaxy, pruning excess star formation, maintaining balance. In others, it might be more like a storm, periodically disrupting the galaxy before settling back into quiescence. Each galaxy has its own personality, its own history, its own relationship with its central black hole. The diversity of galaxies we observe might reflect this diversity of relationships. Some galaxies are actively forming stars, their black holes quiet or absent. Others have shut down star formation, perhaps due to AGN feedback or simply because they've exhausted their gas supply. Still others cycle between active and passive phases, their star formation regulated by their central black holes. Understanding this diversity, what causes it and what it means for galaxy evolution, is one of the great challenges in astronomy. It requires observations of many galaxies, statistical analyses to find patterns, and theoretical models to interpret those patterns. It's a puzzle with billions of pieces, each galaxy providing a clue to the overall picture.